title says, LLMs that think. So recently, something called reasoning models or reasoning LLMs have started to appear on the market, but it's not always clear what they are. So in this talk, I'm gonna demystify a little bit the concept, see what they do, see what they're not good at, etc., etc. So let's jump right in with a definition, right? What is a reasoning model? A reasoning model is essentially, as the name says, an LLM that reasons, an LLM that thinks before saying something. So traditional LLMs tend to directly reply to you without putting too much of thought in what they are doing, while this type of LLM is explicitly designed to not do that, to stop for a second, think about it, and then tell something to you. There are many examples of LLMs like this. Most flagship models nowadays tend to be thinking models because they perform better on very complicated tasks or agentic systems. Back in the days, OpenAI's O family used to be one of the most popular. Interestingly, GPT-4o has an O in the name, but is not a thinking model because the O is the second letter name. But also DeepSeek's R family is a reasoning family. And essentially, every LLM with reasoning or thinking in the name is an LLM that has been trained to work this way. There are also some misconceptions out there. For example, is a reasoning model an AI agent? The definition of AI agent has been a bit fuzzy, but recently we're coming to the conclusion that AI agents are applications that can use tools in a loop to achieve something, right? Which means that indeed, reasoning models are not AI agents per se. Most people tend to use reasoning LLMs a lot in these agents because indeed they are smarter, they think a bit more, but they're not the same concept. So thinking LLMs can be used to build very smart agents, and also agents are built on top of these LLMs. So they are two different levels of abstractions, and this is something that a lot of people tend to mix up. If you're a bit more technical though, you might have heard that reasoning models are just glorified chain of thought prompts. This is a bit more specific because chain of thought is a style of LLM prompt that basically asks the LLM to think step by step before saying something, which by the definition I just gave, sounds like the same thing, right? However, chain of thought prompting is not enough to make an LLM a reasoning LLM. The two concepts are separate. Reasoning models were definitely inspired by chain of thought prompting, but the two are still conceptually different, and we're gonna see why in a few slides. So, in order to understand a little bit where we are at with these different LLMs categories, let's make a little taxonomy, a very simplified one, just to give you an idea of what you can expect when you prompt an LLM, the way they will reply to you. All LLMs, including some models that you won't necessarily consider LLMs, tend to fall under the umbrella of text completion model. So every model that is able to generate the next token, given a string of tokens, a string of words essentially, is considered a text completion model. Early models like GPT-2, GPT-3 also falls under this umbrella. A subset of these models is what is called an instruction-tuned model. This is an LLM that not only just generates the next token, but is trained on purpose to know that the string that it receives in output is a question to be answered. So it's not something to just complete mindlessly, which models like GPT-2 were definitely doing, but it's something to be replied to. And this is what instruction-tuned models mean. Reasoning LLMs are even a subset of these instruction-tuned models that not only consider your input something to be replied to, but they consider your input a question that needs to be reasoned on before replying. So it's even a subset of a subset, and indeed a few models like GPT-5 or 1 or 3 DeepSeek fall into this category. To clarify a little bit, what does this mean? Let's imagine we have this prompt. Calculate the distance covered by a car going 100 kilometers per hour for 3 hours, right? And we give this prompt to each of these models, essentially. When you give this prompt to GPT-2, for example, it will apply something a bit unexpected, because the most likely answer is something that looks like this, on a highway. And why does it do that? Why does it complete your sentence? Because you were missing a dot up there. There is no dot, so the most likely token could be a dot, but could also be the continuation of the sentence. And that's why these text completion models were a bit difficult to use for like chatbot applications. If you take the same prompt without any modifications and you pass it to an instruction-tuned model, the answer is very different. Because the answer looks like this. Certainly, the car would cover approximately 300 kilometers, which is correct, it's great, it's a great answer. However, this is good because the problem is trivial. But what if the problem was very complicated? What if the car was going at very different speeds for a long time, or maybe you wanted some more complicated problem that is not obvious what the answer would be? Well, in that case, you have nothing else to work on because the LLM would only be trained to reply to you something. And also, when you ask it to justify, it will just kind of justify itself, but it will not show you what it was thinking about because it wasn't thinking about anything. It was just generating the next token. Reasoning models have a different approach because when you give the same prompt to a reasoning model, what comes out is something like this. First of all, you have a reasoning phase. In this case, I separated it with like two tags. Normally, the reasoning part would be hidden because in general, you don't necessarily want to see the reasoning. But it would start generating tokens saying, let's calculate the distance with the formula, the distance speed per time, so 100 per 3 equals 300 kilometers. And then it will stop thinking and tell you the car will cover 300 kilometers. So, as a user, normally in the UI, you will only see the car would cover 300 kilometers. But if you are not sure about it, if you want to know how the LLM reached this conclusion, then you can check the reasoning, and you will see how the LLM actually came to the conclusion. You don't need to ask it after the fact to justify what it did. You can check what it did before replying to you. So you know already how it came to the conclusion. So let's go a bit more into details about how do they work. The reasoning process is again two-step. So when the user gives a prompt to an LLM, what happens is that first the LLM reasons and then it replies. About the reasoning stage, there are a few interesting things to know. For example, the output is very similar to what you would get if you were prompting an instruction-tuned LLM as a chain of thought. So you can get something that resembles reasoning models by very carefully prompting an instruction model to do that. It's complicated, it's difficult. So the real difference in here is that the reasoning model does it automatically. You don't have to care about specific prompting, like to care about the wording of your system prompt to get this result. It just gets this result for every possible prompt. Interestingly, the reasoning phase also, in many cases, has a customizable reasoning effort parameter. So what you can do is that you can tell the LLM to think more or think less about the problem. Another thing is that the user, the LLM can give the LLM tools to verify its knowledge during the reasoning phase. So the LLM can invoke tools in a chain to just get to verify its knowledge, maybe to do some web searches, something like this. It can be done during the reasoning phase as well. But the most important thing that some people believe is that during the reasoning phase, there is no sort of symbolic reasoning. There is nothing except the LLM talking to itself to figure out what's going on. So the reasoning phase is not very special in this regard. You don't plug in different tools, you don't plug in a reasoning engine, you don't have strange like code or magical things going on. It's literally just the LLM thinking out loud until it's convinced itself that the answer is correct. So this is basically what's happening during the reasoning phase. After the LLM is satisfied with its replies, it will generate an end of reasoning token, and it will know that it stopped the reasoning. And at that point, it will start to generate the actual answer. The answer, in general, is a summary of what came before. The LLM knows what it was thinking about, so it will essentially summarize or like cut away the important parts and give them to the users during the answering phase. Again, the answering phase is just generating tokens. So again, there are no external tool, no special tooling involved. It's literally just the LLM generating based on what it generated earlier. Okay, so now to go a little bit into even more specific detail, let's see what happens if I pass that prompt to a non-reasoning model, and let's see what are the pros and cons again. For example, how long does it take to drive from Lisbon to Paris? Again, GPT-4 would tell me 20 hours. Okay, is it true? Is it not true? I have no clue. I never driven from Lisbon to Paris, so I have no idea. And this is essentially the core of the issue, right? The LLM just memorize this from training data. You have no idea where it comes from. The LLM cannot tell you because it does not remember. It's unverifiable unless you do extra work afterwards to figure it out. The advantage though is that this is cheap and this is fast. So if you trust your LLM with its facts, for example, you fine-tuned it, or you know that the LLM has maybe done a web search earlier, or if you're using RAG that it kind of grounds the LLM, non-reasoning models still have their niche because they're very fast. Also, if you're really concerned about latency, reasoning models can be challenging because nothing is faster than just replying, right? However, there is a middle ground. For example, reasoning models with low effort. Low effort means simply that you tell the reasoning model to reason a little. Normally, these are just variable parameters, like you can set from 0 to 1, depending on how much you want the LLM to reason. And essentially, when you're telling the LLM how much to reason, you're telling the LLM how much it needs to talk to itself before stopping. So for low reasoning, I would expect a little bit of like a paragraph worth of reasoning. For like a high effort, instead I would expect maybe a page or something like this. In this specific case, what it would do is that first of all, it will ask itself how far Lisbon it is from Paris. It will try to figure out the distance, then it will calculate the speed using the formula again, then it maybe use the calculator to make like the actual calculation and come out with a different number. This is 15 hours. So which one was correct? The 20, the 15? I mean, surely this one looks a bit more grounded. We know what's going on, we know how we reached this number. But the LLM also took a lot of assumptions here. For example, you use the speed limit, you can check in the reasoning, you just use the speed limit to calculate the time it took. But you know, that's not a great assumption to make. Most people doesn't go at the full speed limit for the entire ride. So you can check in here that the number maybe is not that accurate. And you know this because the LLM will tell you how we reach that conclusion. So again, it's better because it reasons from like first principles, you know what it's doing. But again, it relies on memorized figures occasionally, and it does not challenge all the assumptions it's making during its reasoning phase. If instead you go into high effort, it is much more likely that the LLM will generate something even much bigger than this, to be honest. It will calculate the distance, it will double check all the speed limits essentially, it will do all this reasoning, and it will also like ask itself several times, did I do this right? And sometimes, for example, you can find occasions in which the LLM catches itself. Ah no, I made a mistake. You can find occasions like this in the reasoning trace because the LLM has time and has the motivation set by the high effort parameter to think more, to like read again what it did, like think a bit harder. And in this case, it's interesting because this answer, it takes 15 to 20 hours. It's actually the most reasonable. It's such a long distance that you don't have a fixed number. The LLM should not just give you 20 hours. It's much more reasonable that it gives you a range. And the LLM reached this conclusion because it was thinking about it hard enough. Again, the disadvantage of this is that this is slow and expensive. So if you're, for example, developing a voice AI application and you're on the phone with your client, this is a hard sell. This is gonna be difficult to implement in a way that is fast enough to make it really work. There are compromises, of course. You can lower the effort or you can do it in another way. But this is great if you're not concerned about latency. If you, for example, want your LLM to do a code review, something like this that doesn't have like any time constraint. In this case, it's great because the LLM will really challenge itself until it comes to a conclusion that makes at least itself happy. Nice. So when to use that? I think we already kind of covered that. Again, if you're concerned about speed, low cost, or are you executing well-defined tasks, you're relying on stable facts, for example, you have RAG in front of your LLM, not necessarily a reasoning model. Like, you don't necessarily need it. Consider it because it has trade-offs. When you need accuracy and reliability, you need to be able to audit what happened, you need like self-corrections, you need a bit more complex problem solving, then reasoning models are definitely the way to go. Okay, one last note about this is that introducing thinking into an LLM kind of enables a new scaling law. What does it mean? This means that so far, before the introduction of thinking models, the only way to make an LLM smarter was to make it bigger. So more training data, more parameters, more compute, whatever, but bigger in terms of parameters, right? With the introduction of reasoning, now there is another way to make it bigger, which is to make it think for longer. So an equally big LLM, by thinking harder, will give better answers. And this enables basically two different directions in which to grow the intelligence of an LLM. And this means that essentially LLMs are going to become smarter without growing as big as we would expect according to the previous scaling trajectory. Which is nice because it means that basically you can, for example, self-host smaller LLMs that are equally smart as older models. And that's kind of it, actually. So thank you for hosting. That's all. If you have questions. I think he was first.
You mentioned that reasoning LLMs are not the same as agentic.
Yes.
But then you described the reasoning LLM doing the same thing that an agentic does.
That's
so
interesting.
What if you
yes.
have a agentic AI that doesn't reason, but then you run it as an agent and have it repeat the steps of what it was actually thinking about?
Interesting question. Very nice. Indeed, the line is blurry in terms of the final result. So you can, if you think hard, if you try hard enough, you can make an instruction-tuned model, like a non-thinking model, to behave like a reasoning model. In the same way in which you could make GPT to actually reply to your question with an answer by just making sure that the question mark was there. So it's not about basically something that the instruction model could not do at all. It's about basically the effort you need to put into it. Reasoning LLMs do it out of the box. They always do it, regardless of how you prompt it. So you, for example, you have more space in your system prompt. You don't need to care about putting all the chain of thought instructions into the system prompt because the LLM does it automatically. So it's about simplifying the way you prompt it and kind of guaranteeing your answer as well. You're guaranteed with a reasoning model that you always have the reasoning. With an instruction-tuned model, you don't.
Okay, but then you can also customize the level and type of reasoning.
Yeah, exactly. I mean, it depends. Like there are trade-offs. Okay. The lines are blurry. Yeah. Please.
Can you talk about the fine-tuning or how they train? Is it like instruction, except the examples have reasoning examples?
Essentially, yes, there are post-training steps. Now in here it would be too complicated, and honestly, I'm not too an expert in how they are fine-tuned. But yes, they basically have a post-training step where they really enforce the reasoning procedure on them. It's not part of the classic fine-tuning, it's rather a step on top.
Okay.
Yeah.
Maybe like reinforcement or something.
Yeah, it's more like reinforcement learning, exactly. Oh, please.
Can I say that a reasoning model in a way is we are letting an LLM to hallucinate in its own sandbox, and then we summarize the latent space discovery across different iterations and give an output?
So yes, in a way, yes. We hope that it doesn't hallucinate too much during the reasoning step, of course. But in fact, actually, it's a good way to put it because during the reason, if the reasoning is long enough, the LLM has time to figure out that, okay, maybe I hallucinated here because indeed, you probably know how LLMs work. Basically, they condition the next token according to all the previous tokens they generated. So essentially, the LLM does look back while it generates the next token by using the attention mechanism. And the more tokens it generates, the more likely it is that it notices that it hallucinated earlier. So that's why giving it more time to reason, more tokens to generate essentially, makes it more likely that this thing is spotted, and the LLM will have this moment like, I made a mistake, let me correct it.
Right.
Yeah.
Right. And the second question to that, the effort that is being as a parameter for the reasoning duration, can we also say it's similar to the temperature for an LLM, saying that how much can it deviate from its
Yes and no, I would say. Then the temperature is more about inserting randomness into the output, right? So it's more about letting the LLM make more mistakes in a way. It's actually, you could say almost the opposite, because the temperature is about letting the LLM try something that is low probability, experiment a bit, try tokens that will not be picked otherwise. While in reasoning it's the contrary. You accumulate enough tokens that essentially the probability kind of homogenizes over the entire response, and then it becomes, let's say, less likely to have something that is out of distribution a lot. So the idea is a bit opposite, I would say, even.
So inversely proportional.
Sorry?
Inversely proportional to that.
I would say yes.
Okay, great. Thank you.
Please.
Can you explain a little bit better the part of this new scaling law?
Right.
Why is these models are make better replies?
Okay.
Can you just to refine?
Yeah. Okay, so especially at the start of this LLM's development, an easy way to make an LLM smarter was to make it bigger. So, for example, an LLM with 8 billion parameters was strictly dumber than an LLM with 70 billion parameters, which was dumber than one into 120 billion parameters, etc. So by increasing the size of the LLM, it was one simple way to make it more smart. Of course, then there were other methods. You could also increase the quality of the data. You could increase the amount of data you train it on. So there were different ways to make the LLM bigger, but essentially, it always boiled down to have more parameters. So bigger parameters, maybe better used, but the more, you just needed more of them. With the introduction of reasoning, the same LLM can be let talking for longer. And just by doing that, without changing the size of the model, without changing its training essentially, the LLM will give you better reply by just talking for longer. So this is, let's say, a different way of making an LLM smarter, and you can see that in the benchmark, the same LLM, properly trained, but the same LLM with lower reasoning effort and high reasoning effort was actually getting better results. So that's what I mean by another scaling law. You can scale it, but making the LLM better at reasoning, or by reasoning more, but you have another direction in which to make this LLM bigger, which is not directly related with the number of parameters it has, which is nice because the LLMs with more parameters also need a bigger GPU to run. So it's nice that you don't necessarily need to make it bigger in order to make it more intelligent.
So reasoning is not exposing the thinking, right? Because the reasoning is not the same that exposing the thinking, because the system, the chat 4.0 that you said is not the reasoning, but could be a reasoning, but not expose the thinking, right?
It was all in the internal parameters. Yeah.
Okay.
Yeah, right now instead is like explicit. The LLM talks out what it's thinking about in a way. Yeah. Please.
I have a more philosophical question.
Interesting.
So how similar or different is it to how humans learn things? And are they getting inspired perhaps by that process?
About learning, I'm not sure, but about, for example, solving a problem, I would say it's getting closer because, for example, imagine when I'm calculating how long it takes to go from A to B. I don't just know the number directly. I sit down, I think about it, like maybe I write down a couple of numbers, and then I come to a conclusion. So in terms of solving problems, I would say that the thinking process is for sure inspired by that. Then, of course, with LLMs, it's always a bit tricky to say, is it thinking like a human, it is not. The way it works is very different, so it's hard to tell. But at least the approach of at least solving the problem, if not learning how to do that, but to do it in practice, I find it much more similar and also much more understandable. So it's more comprehensible what's going on because you can just look at it thinking out loud in a way. Please.
President, this thought. If you're thinking a lot about some problem, sometimes you make it worse. So yeah, is it something with LLM when it's over reasoning?
Oh yes, actually that's a very good point. One of the reasons why I said earlier that you should not, ideally you don't need to use a reasoning LLM for a small task, is that they overthink it. It can happen. If you have a very simple task that it requires no consideration, the LLM sometimes will overthink it. It's better to use GPT-4o if the answer is very simple, because the LLM can do it. And interestingly, that's one of the reasons why this low effort reasoning and high effort reasoning even came to be. Because you could imagine, maybe I want the LLM to always think hard about the problem. But no, sometimes you actually want the setting to be a bit lower. And interestingly, I think this is kind of the idea behind the GPT-5 current UI, you know, that you can set it to really think hard, because automatically the system will try to set the reasoning effort that it thinks it matches better with your question, which it doesn't always work very well, but that's the idea.
I would add on the last question. Are there any models that actually are able to differentiate if they need more reasoning, or they're able to do it with low reasoning?
Good question. I think so. As far as I know, there are no models that can do this internally. So you have to set the parameters, as far as I know, but research may have gone ahead since I checked last time. What I know is happening, for example, on GPT-5 specifically, is that there is an external system that kind of checks your query, second guesses what is the best reasoning effort, and then routes it to the model that it's configured appropriately. So yes, it's done before sending it to the LLM. Please.
You mentioned that there's no symbolic reasoning. What do you mean by symbolic reasoning?
Yes. Like once I came across a person that believed that LLMs can play chess because they have a chess engine inside. And this is what I mean by no symbolic reasoning. That is not the case. There is not a chess engine inside the LLM playing chess for you. So there is no such thing hooked to an LLM to make it reason better. The LLM just reasons by talking. So that's what I meant by no symbolic reasoning, essentially.
I don't get it.
Okay, let me try again.
You mean like it doesn't have an image of the chessboard with the current pieces on it at the
Oh,
time?
no.
Or something
They
else?
thought that do you know about Stockfish, the chess engine? But there is basically a program, a completely deterministic program that is able to solve chess problems. And some people thought that LLMs are only able to solve it because they have access to this chess solver, or like a logic solver to like do math. Or they can only do math if they are hooked to like a Python interpreter. That's not true. They can do all this stuff by just talking. Whether you want them to do this or not, that's another matter. But there's not, like reasoning is not offloaded to something that is deterministic and that it's outside of the LLM. The reasoning happens by the LLM talking. That's kind of what I meant. I don't know if that's...
Just what it knows from the neural connections, I guess.
Yeah, exactly, yeah. Just as it generates all the rest, essentially. It's not special. Yeah.
Yeah, so I can comment on that. So these AI models, they don't deduce from one step to the other, they just infer. Right? When you said symbolic reasoning, that means you have deduction rules. So say like in math, right? You have a definition represented by a symbol, and then you have rules, like fixed rules, right? And we deduce to go from one step to the other by logical reasoning. This is what the models do not do. Right? But it's now baked into the weights, so to say, because they have learned to remember the right deduction steps. Right? But it's not as in a computer program, for example, that you have a fixed rule. It has just learned how to go from one step to the other. But it's still inferred, so to say.
Thank you. Very nice. Please.
Do you know how far, I know that there have been some research attempts at making this reasoning in a random language or random tokens that are not, do you know how far they've done this? Is there anything?
I think I just heard about it, but I haven't really investigated much. I know that some people find value in the reasoning trace, so making it like optimized for the LLM by using special languages or special token will kind of avoid a little bit the advantage of having it in the first place. So I suppose that's why I didn't hear too much. I don't think it's being pursued, at least in the major models, but I'm not sure.
Can I make a comment on that? 'Cause
Sure.
I think in the AI safety space, a lot of the people, they think the best way we have right now to kind of control the AI is to look at its reasoning trace.
Yeah.
So
Also.
if we obfuscate that, then
Yeah.
it's kind of fucked.
Exactly. Yeah. That really, it helps to have that trace. It's sort of a byproduct, but it's also not. Like sometimes it's really useful to have.
There was a recent podcast presentation was OpenAI, where they keep running into an issue where AI keeps trying to develop its own language to reason.
Oh, I haven't seen that.
And they keep forcing it to reason in English or regular so they can figure it out. But supposedly ChatGPT 6, they decided to let it use its own language because it will be a lot more efficient and quicker at doing that using its own speed up things as opposed to trying, because
Yeah.
normally it has to convert everything to English,
Ah,
do
okay.
the reasoning, and then convert it back. And they're hoping that that'll speed it up, but at the same time they'll be able to monitor it based on the outputs or something.
Ah, that's very interesting. Maybe I will ask you to share the link later.
It was on YouTube.
Ah, then okay, I'll look for
Search
it.
for a recent OpenAI version.
Yeah. Any? Oh, please.
Sorry if this is a stupid question.
No?
Do you think these reasoning models could be applied in other areas of the AI, not only the LLMs? Because you are talking about this law, scaling law could be the old scaling law. It's no longer valid. Can we use the reasoning in other areas of AI?
You mean like something that is not LLM specific?
Yes.
Mm,
They
okay.
are LLM.
Very interesting. I would say an approach like this could be used to any decoder-only model. So any model that taken a string generates the next characters or words, then maybe you can think about using an approach like this, because essentially you're just making the LLM make a longer answer in a way. So as long as you have an LLM model that does that generates tokens one after the other, so that it sort of like thinks about what will be the next word by looking at the older ones, in that case, this approach works. Other completely different reasoning models like classifiers, they are already like, I think, they just don't work this way simply. So this is not an approach that works. For example, if you were using an embedding model like BERT could not really be adapted to work like this because BERT does not generate the next token. So it cannot be convinced to like think longer. It's something that happens after the generation, not inside the model itself.
My question is because I'm working in some work, let's say, on the image generation. So the diffusion models, meaning that I'm degrading the image, and from the very bad image, I could try to understand what could be the perfect image from them. Could be this used on this field?
That's the next talk.
I think this is cutting edge research if it exists, so I'm not aware of any approach, of anybody that tried. I'm not even sure if it could work because I think diffusers work in an essentially different way, just like BERT as well. But I don't know.
The first issue I see with that is a reasoning model understands the text that it puts out, whereas imaging does not understand the image unless you actually had a vision model that could look at the image.
Yes, but the vision model, it's the image is a pixel, not a pixel.
There are approaches that, I mean, it's possible. For example, the latest DeepSeek OCR, that one works with basically visual tokens. So technically it is understanding the image in that way. But
It can be done.
yeah, it can be done, but I find it like difficult, and I don't know if anybody has done it yet. So yeah.
Good project for the future.
Think about it, like next talk really.
Yeah, no problem.
Anyone else?